So I would like to thank you for giving me this opportunity to present my work. So starting with the today's topic, it is related to object-based image analysis for glacier feature extraction from digital remote sensing images. So this is my PhD work. So I would like to thank my PhD guides from India, Sanjeev Sofat and Manoj Arora, and also my mentor, Reet Kamal Tiwari, because this particular work is his idea. So to start with, uh, to start with, first I'll be highlighting what are the major, glacier features or glacier cover classes, as they are commonly called, that are present on the debris cover surface. So as you can see from this particular image, this is a Gangotri glacier. So this is the main trunk of the Gangotri Glacier, and it lies in the Indian Himalayas. So from this particular accumulation zone, you can see that there are certain features which are very spectrally similar. So this SDD is known as supraglacial debris, which is present on the glacier surface, and PGD, that is periglacial debris, that is present outside the glacier boundary. It is found at the margins of the glacier. So these two features are formed from a common source called as valley rock. You can see here from in the, I would say, the ablation zone, which is very near to the snout. And that's why it becomes very difficult to spectrally, separate SGD and PGD. Also, you can see their ice mix debris that is called as IMD. So it is a mixture of ice and debris that is present on the surface. Snow ice is, as usual, represents the clean ice part of the glacier. Then there are other different features that are called as exposed ice faces, also commonly called as ice cliffs. So presence of ice cliffs, melts the debris cover part of the glacier. And there are other features like debris cones. These are the conical sediments that are deposited, uh, and they play a critical role in the development of the debris cover glacier. In this ablation zone, you can see the crevasses. These are the fractures on the glacier surface, and they really pose a problem for field expeditions and other travelers. Then there is also there is one feature called as rills. So this is a narrow channel formed on the debris cover by the water surface, flowing water, I would say. Uh, and these rills form the main drainage channel for the debris cover glacier. Then there is a meltwater stream, so it flows from the snout towards Gangotri. So there's a district called as Gangotri as well. So downstream, this stream flows towards that particular village. So all these features have some or the other significance, and therefore accurate extraction of these features is really very important. So coming to the method, that is object-based image analysis, which is also referred commonly as OBIA. As we move from coarse resolution to high spatial resolution images, the small size features are also visible on the small size glacier features are also visible. And therefore, the high spatial resolution images reveal the real world objects, and they provide the real world scenario. Along with the spectral information, the high resolution images also capture the shape, texture, and context. These are nothing but the spatial information. However, the pixel-based approaches that are in which the basic entity is a pixel, they fail to utilize the spatial information, and therefore object-based image analysis, that is OBIA, came into play. Because OBIA works on a group of homogeneous pixels rather than a single pixel. So coming to the OBIA process, the beauty of OBIA is that we can work on, we can extract the different glacier features at different levels, meaning that if I want to extract the large size glacier features at one scale and the small size features at another level, then I can do that using the OBIA. And also we can give input from different sources, multiple sources to the OBIA. So the first step in OBIA is to define these primitive parameters. They are known as color. Then there is shape. So shape is formed by smoothness and compactness parameters. Then there is also a scale parameter. So scale is an abstract value, and it also depends on the spatial resolution of the image. So these user-defined parameters we can select based upon the study area that we are considering and also the kind of glacier features that we want to extract. Once these features are defined by the user, it is followed by the image segmentation process. So in my study, I have used multi-resolution segmentation, which I'll be discussing in my next slide. After image segmentation, the image objects, we get the image objects at different scales, as I said before. So at a coarse resolution, I can get the larger size glacier features, and at a fine scale, I can get smaller size features, like say, for example, the ponds or the crevasses, and so on. This is followed by defining a class hierarchy. So how do we define a class hierarchy? It is based on, say, for example, I have a debris cover that is the supraglacial debris, SGD area, and the lakes are formed on this surface. So SGD will become the parent class and the lakes will become the child class. So this is how a class hierarchy establishes a contextual relationship among the different glacier features. Then these features are extracted using classification. It can be done using rule-based classification, or simply using nearest neighborhood classification. Thus, we arrive at a classified map at different scales and followed by the accuracy assessment of the thematic map. So coming to the image segmentation, that is multi-resolution segmentation. So it is based on a mutually best fitting approach, meaning that first it starts with with one pixel, and this one pixel looks for a best neighbor depending on the homogeneity criteria that we are defined in this particular step, that is this user-defined parameters. So this will define the homogeneity criteria. So, and this process continues till that particular object finds a best neighbor. Once it finds a best neighbor, it merges with that best neighbor, and this iterative process continues for other objects. So while we are going through the image segmentation, we need to handle two types of errors, that is under segmentation error and over segmentation error. So we need to arrive at an optimal segmentation like this, meaning that the segment that is formed from the image segmentation needs to fit well with the object that we want to extract. So here I have taken an example of a glacial lake. So in case of under segmentation error, the size of the image segments is very small compared to the objects of interest. Whereas in case of over segmentation, the size of the segment is large compared to the object of interest. So, but we can deal with this under segmentation error because as can be seen from this image, these segments can be merged. But if we go for over segmentation, then it becomes very difficult to deal with over segmentation error. So this is all about image segmentation. Then the rule sets are formed for performing the classification. In my study, I have used the rule-based classification because of certain advantages of rule-based classification. So we can form complex complex class descriptions here, and also these rule sets are transferable. This is not the case with nearest neighborhood classification. So I've considered an example here. Say if we consider the SGD class. So as I said before, that the SGD forms the glacier surface. So because of the underlying ice, it has a lower temperature compared to the non-glacier surface, say the PGD and the valley rock. So I will consider this particular attribute to form a rule set, and based on the analysis, if I consider the value of this particular SGD class, say consider it can lie between 0 to 260 brightness temperature value. Then the rule set would be if brightness temperature of that particular object belongs to this particular range, that is the low brightness temperature mean value, that is 0 to 260, then that particular object will be classified as SGD. So similar way we can form different rule sets, define rule sets to classify one particular glacier feature. And thus a combination of rule sets can be used to describe one particular glacier cover class. Also, the output of one fuzzy rule can go as an input to the next fuzzy rule. So thus a well-structured hierarchy can be formed. So these are some of the noteworthy works that I would like to refer here. They have utilized object-based image analysis for glacier feature extraction. All this work is on debris cover glacier, on different debris cover glaciers. If anybody is interested, please go through those papers. However, the limitations of these studies is that these studies are solely based upon utilizing the spectral information, whereas OBI has much to offer than just the spectral information, but we can also utilize the spatial information of the images. And also these studies are based on medium to coarse resolution images like say Astro and Landsat images, and therefore OBIA, which is found suitable for extracting information from the high resolution images, would not, may not have found the real usage. Also, a few of the studies have done the manual digitization of the shadows and the valley rock because of the very fact that these have the shadows actually have a very spectral similar reflectance with the glacial lakes, and therefore manual digitization needs to be performed. So these are the limitations. And also one point I would like to highlight here is all these studies have utilized the traditional pixel-based error matrix, which is not considered valid for assessing the accuracy of OBIA-derived classified maps, because in OBIA, the basic entity is not a pixel, but a group of pixels that is objects. And therefore, we really need to consider, we need to modify the traditional pixel-based error matrix. So the study area that I have considered here is the Gangotri Glacier, which lies in the Uttarakhand district of the Indian Himalayas. So as can be seen from this particular image, this is the snout, and this particular area forms the Gangotri district. So this snout is approximately 18 kilometers from the particular Gangotri village. It has 4 major tributaries, and this is the lower ablation zone of the glacier, this is the mid ablation zone of the glacier, and this particular portion forms the accumulation zone of the glacier. So the glacier flows from this to the snout, and it flows from northwest towards the northwest direction. It is also one of the largest glaciers. No, not the largest, I would say the longest glaciers, having an approximate length of 30 kilometers. So I've also chosen this Gangotri Glacier because of its because in India it has a spiritual importance. So coming to the remote sensing data sets, I have used different high spatial resolution images to design an OBIA methodology. So one is like worldview 2 data, which has a multispectral resolution of approximately 2 meters and a panchromatic resolution of 0.5 meters. So worldview 2 image pertains to the Gangotri Glacier, and I've also considered another debris covered glacier, that is Badashiri Glacier. Then the second image that I have considered is Indian remote sensing satellite data, that is LIST-4, which has a high spatial resolution of approximately 5 meters. This particular image pertains to the Gangotri Glacier. Along with this multispectral data, I have also considered ancillary data in the form of brightness, temperature, and slope to correct the glacier boundary. And also, as I highlighted before, the glacier surface and the non-glacier surface has some spectral similarities, and therefore ancillary data helps to discriminate among the non-glacier surface features and the glacier surface features. So it is a very common phenomenon in glacier mapping to compare the glacier boundaries with the Randolph Glacier inventory. So apart from Randolph Glacier inventory, I've also manually digitized the glacier boundary using the pan-sharpened very high resolution worldview 2 image of 0.5 meters. So this forms my reference data. The software tool I have used for designing the OBIA methodology is the Tramble's eCognition software tool. So I have performed 3 different experiments. So first experiment pertains to the worldview to image plus ancillary data set. And this in this experiment, I have considered Gangotri Glacier. Then second experiment I have second experiment I have considered Gangotri Glacier, but I have considered different sensor data having different spectral properties. So that is LIST-4 image plus ancillary data. And in the third experiment, I have kept the worldview 2 data set as it is, but the study area is considered as the Badashiri Glacier. So coming to my first experiment, an in-depth spectral analysis was performed using the worldview 2 multispectral image. As can be seen from this particular spectral plot, it is observed that the SGD and the PGD classes here, you can see that it has a very similar spectral pattern. And there are other features like the exposed ice faces and the glacial lakes, which also share a very similar spectral pattern. This is where, the ancillary data is going to help to discriminate among features. So, as can be seen from this particular brightest temperature graph, this SGD, which has a low temperature, it is showing a low temperature for the SGD. Then the PGD class. So sorry, this is the PGD class, and this is the snow ice plus IMD class. So this is the snow ice IMD, which obviously will have a lower temperature compared to the SGD. And the PGD, of course. So Valley Rock will have the highest temperature because it is formed, because it is completely formed of rocks, and therefore it will have a higher temperature. So same is the case with the slope. As can be seen, SGD is formed at a lower slope compared to the PGD, and PGD is formed at a lower slopes compared to the Valley Rock. So these two particular ancillary data sets are going to help discriminate between the glacier surface and the non-glacier surface features. So after a trial and error analysis, I arrived at 2 optimal scales, that is 260. So at the scale 60, I have extracted the large size features like the SGD, PGD, and the Valley Rock, and also the IMD, that is the ice mix, debris, and snow and ice. At scale 60, I have extracted the smaller size features like, say, the glacial lakes, and also the crevasses and the rills and so on. So the shape and the compactness remains the same for both the scales. So this particular figure shows why I have considered the ancillary data. So as can be seen from this particular subset, here it is very difficult to distinguish between this is a SGD and this is a PGD. So it becomes very difficult to distinguish between these features without the ancillary data. So after considering the ancillary data, we can, it can be seen that the SGD and the PGD area can be effectively segregated. These particular two figures define the scale at which I have extracted the different size glacier features. So as can be seen from this particular subset D, this shows that the glacial lakes. So at scale 60, the lakes can be extracted optimally, but this is not the case with this coarser scale at 200. So this is about the segmentation, and I have evaluated different attributes to extract the different glacier features. So these include the mean and the standard deviation. So mean and standard deviation represents nothing but the spectral values of all the glacier features. So all these mean and standard deviation values have been used for preliminary classification of these glacier features. Then, based on this preliminary classification, other attributes have been used to differentiate or distinguish the different features. So for example, say I have used the SDI, which defines the shadow detection index to map the shadows and the exposed ice faces. Then I have used the max difference attribute to map the glacial lakes. I've used the GLCM mean to map the crevasses. All these attributes that I've listed here, they have been carefully evaluated. And also I have sought an expert advice for after getting the results. So this is the complete methodology. So as I said before, at scale 200, the SGD, PGD, the valley rock, the snow ice, IMD, and also the shadows have been extracted using the not just the spectral information, but also the ancillary information, that is brightness, temperature, and the slope. Then the smaller size features have been extracted using this spatial information attributes at scale 60. So this is the large scale glacier cover map. This is the output of the previous methodology. I have also, so after comparison with the original image, we can see that the classification has come out pretty well. But here, if you could see the reels, there are some other reels as well here, which are very small, that could not be extracted here. And also few of the exposed ice faces here, they have been misclassified as glacial lakes. So because of the spectral similarity. So coming to the accuracy assessment of this glacier cover map, uh, I have uh, uh, I have actually assessed the accuracy using traditional pixel-based error matrix, and the results are quite good. However, the question again arises, is this matrix suitable for OBIA? So since the reference sample units vary in size, in case of OBIA, these particular traditional error matrix is going to give me a dissimilar accuracy estimates. And therefore, Radox and others in 2011 designed an area weighted error matrix specifically for assessing the accuracy of OBIA derived classified map. So here what happens is like the modification is very simple. I'll go to my next slide. So this is the formulation of the area weighted error matrix. Here the reference sample units, that is each segment has a different size. So the sample, every sample is being weighted by its area in the traditional error matrix. That is the simple, variation that has been done in the area weighted error matrix. So after adapting the area weighted error matrix and comparing it with the traditional error matrix, it was found that the accuracy has been improved significantly to 93.6% from approximately 89%. So it means that the traditional pixel-based error matrix underestimates the accuracy of the OBIA derived maps. So that's why it's very important to evaluate the accuracy of the OBIA classified map using the area weighted error matrix and not just simply the traditional error matrix. So as I said before, I have evaluated the glacier boundary derived using OBIA with the manually digitized reference boundary and the Randolph glacier inventory. I would like to highlight here that the RGI boundary is generated using the medium resolution data set of Landsat and Aster, and therefore the results which I have got here after comparison say that uh, the RGI, the glacier boundary that has been extracted here matches closely with the manually digitized one, then the RGI one, because RGI has certain uncertainties because it has used the medium resolution data set, whereas the manually digitized glacier boundary has been created using a very high resolution imagery of 0.5 meters. Coming to the second experiment, so I have basically adapted the previous methodology that has been defined in experiment 1 to apply it on the list4 image plus ancillary data sets, again considering the Gangotri Glacier. So this is the list4 image. You can see that because of the resolution of the list4 image which is 5 meters, certain features like the crevasses and the rills could not be visible in this particular image. So, and therefore some of the rule sets that have been defined in experiment 1 needed to be modified for. Also, list4 does not have the same number of spectral bands as the Volvo2 image. So because of the absence of coastal blue and the yellow spectral bands, I had to modify some of the rule sets. So here is the modified rule sets that I have adopted for classifying the list4 imagery of Gangotri Glacier. Uh, the accuracy assessment reveals that the PGD, which forms at the glacier boundary, is the accuracy of this PGD class came quite low, and also same is with the Valley Rock. But since this is a non-glacier surface, it does not have any negative impact on the glacier boundary delineation. So we can ignore it. Then coming to the experiment 3, I have considered the Bada Shigri Glacier, keeping the data set same. So, however, since the study area is changing here, the brightness, temperature, and the slope information will definitely change. And therefore, some of the rule sets, like for example, pertaining to the SGD and the PGD, the Valley Rock and Snow Ice and IMD, which are particularly based on the ancillary information, needed to be modified here. Then the accuracy assessment using the area weighted error matrix reveals that the exposed ice faces, that is the ice cliffs, revealed a very low accuracy. This could be due to the very fact that I'm using the brightness temperature here along with some other rules set to classify the exposed ice faces. And since brightness temperature has been considered uh, has a very high, low spatial resolution, it might not be fitting well with the exposed ice faces. So again, here also the comparison of the glacier boundary with the RGI and the manually digitized reveals a close match with the manually digitized one compared to the RGI one. So coming to the summary and conclusions, Since I have allowed a high weights to the temperature and the slope data, it has facilitated the creation of optimal segments for the spectrally similar glacier cover classes like the non-surface, that is PGD and Valley Rock, and the glacier surface, that is the PGD. So here I've not only emphasized the use of spectral attributes, but I've also emphasized the use of spatial attributes for the spectrally similar small size glacier features like the crevasses and the glacial lakes and the ice cliffs. Also, I have classified the shadows independently of any kind of manual corrections. Uh, the glacier boundary has been automatically delineated with improved accuracy, and also it reveals a close match with the manually digitized one compared to the RGI one. The rules that have been defined in this study could be transferred to another study area, say another debris covered glacier, considering the image resolution and the scene conditions and also the season dependent modifications. So this particular study also has certain limitations. So for example, I have used the ASTER data from ASTER DEM having a spatial resolution of 30 meters, and also the thermal infrared data having a spatial resolution between 60 meters to 100 meters. So if a higher resolution DM and a higher resolution thermal infrared data could be used, this would enhance the quality of the OBIA results. Also, since in OBIA, we need to modify the rule sets depending on the study area, if it can be integrated with the deep learning techniques like the CNN or the random forest, it would likely improve the feature extraction of the glacier features. So this particular work has been published in three different journals. So one is like IEEE J-Stars, which is in which I have exclusively worked on the extraction of glacial lakes using OBIA. Then another is the extracting all the debris covered glacier cover features using OBIA. And the recent one is I have worked on the change detection and establishing a relationship with the variations of the glacier features with the climate variables. So yeah, coming to the acknowledgements, I would like to acknowledge the Department of Science and Technology, Government of India, for sponsoring my study. National Remote Sensing Center, a lab of ISRO, for providing me the list for images, digital globe for World View to image, USGS for the Landsat images, and NASA for the Aster images. Yeah, that's it. Thank you for listening. So I can, if we have time, I can take up some questions here.
Thank you very much indeed. The way that we usually do it is we ask people to indicate in the chat or to raise their hand if they have a question, and then we get people to unmute and ask their question directly to you. So does anyone have any questions? Certainly, it seems like a really nice set of results for all sorts of things. Mapping structures on surge-type glaciers was one of the things that I was thinking about when I was listening to your seminar.
Yeah.
Are there any questions, Roger?
Yeah, thanks very much for that talk. That's a fantastically thorough sort of statistical analysis, really impressive. My first thought was you include topography just as slope. Perhaps I don't have a good feel for the resolution of the topography data, but do you think there might be scope for including something more than just slope? So something like roughness and other attributes as well to improve things yet further?
Yes, thanks, Roger. I mean, this is a very important question you have brought up. So yes, the slope information that has been derived using not very good resolution. So I have used the ASTER data, and perhaps not only slope, but probably say consider, as you mentioned, the surface roughness or the curvature or the aspect could improve the results further.
Smashing. Thank you.
Yeah.
Are there any other questions for Kavita? Paco, you
Yeah.
look like you're about to ask a question.
Yeah. I have I forgot to raise my hand. It's a simple question. Is the fact that you have used data from the Himalayas, do you think
Yeah.
this implies any kind of bias? I mean, would you expect similar results and conclusions when applied to debris covered glaciers on some other regions?
Yeah. So I have shown in my results. So I've considered a different debris cover glacier, keeping the methodology same, and I've transferred that methodology for extracting the glacial features of another debris cover glacier, that is the Badashigri Glacier. But yes, it's a very common phenomena in glacier cover mapping that when the study area changes, we need to modify our methodology accordingly. So yeah, so when we are considering another study area, uh, this particular method can be transferred with some variations. In the rule sets, depending on not just the study area, but also the spatial resolution of the data and the spectral properties of the data that we are considering. So yeah, I mean, that is the limitation of this particular study. Yeah.
Okay, thank you.
Yeah.
Are there any other questions for Kavita? I was interested to hear a little bit about your plans for sea ice. Are you using similar techniques for your study of sea ice moving on to?
Not similar, but I am progressing on the deep learning. So I would be using not just, the OBIA. I'll look into the machine learning and the deep learning methods for CIs type classification. So, because OBIA needs really need to be, we need to modify the thresholds that we are using in this particular method. So if we really need to have, better pattern recognition, then deep learning is the solution to it. So yeah, I'm looking forward to that work.
Fantastic. Roger, did you have a second question or?
Yeah, I think Clark is there.
Yeah.
Roger has raised his hand.
I kind of had a half-formed one, which is why I put my hand down quickly because I wasn't quite sure how to ask it. But
Please go
I'll
ahead.
have a go. Early on in your talk, you were describing how your process looks around its various neighbours to find good matches.
Yeah.
I wonder if any information is somehow kept about the quality of the match to the ones that it's rejected, and whether that feeds into something like directionality. I mean, obviously the final shape is going to lead into directionality, but if it somehow says, oh, this one in this direction is the best, but actually the others nearby are pretty good, that might hint that you perhaps want to finalize on a different shape.
Yeah, so actually, this particular multi-resolution image segmentation, it's very random. So there's no specific criteria basically to start with. So there is so it starts with some 1 pixel size, and it has nothing to do with the direction. So it considers the user-defined homogeneity criteria. So for example, if I have defined the scale as say 100 and the shape as say 0.5, and say the color I have defined as say 0.5 again. So it will based on this criteria, it will look for the best neighbor and keep on iterating until the homogeneity criteria is met. So that is what is mutually best fitting approach. So it has nothing to do with the direction. So it just randomly, looks for the best neighbor. I hope that answers your question, Roger.
Yeah, smashing. Thank you.
Yeah. Yeah.
Okay, well, if there are no further questions for Kavita, I think it just falls to me to say thank you very much indeed for a fantastic presentation, and to say that next week at the same time we have 3 early career researcher talks. So there is a seminar next week, and it is early career researcher talks. So we hope to see many of you there. So thank you very much again, Kavita.
Thank you,
Very
Tavi,
interesting
and
talk.
thank you everybody for joining me. Have a good time.
Thank you. Bye.
Thank you.
Bye. Thank you.